Hi, and welcome to an illustrated guide to LSTMs and GRUs. I'm Learn Vector, and I'm a machine learning engineer in the AI voice assistant space. In this video, we'll start with the intuition behind LSTMs and GRUs. Then, I'll explain the internal mechanisms that allow the LSTMs and GRUs to perform so well. I'll follow up with an example. If you want to understand what's happening under the hood for these two networks, then this video is for you. LSTMs and GRUs are the more evolved versions of the vanilla recurrent neural networks. During backpropagation, recurrent neural networks suffer from the vanishing gradient problem. The gradient is the value used to update a neural network's weight. The vanishing gradient problem is when the gradient shrinks as it backpropagates through time. If a gradient value becomes extremely small, it doesn't contribute to much learning. So in recurrent neural networks, layers that get a small gradient update doesn't learn. Those are usually the earlier layers. So because these layers don't learn, RNNs can forget what is seen in longer sequences, thus having short-term memory. If you want to know more about the mechanics of recurrent neural networks in general, you can watch my previous video, An Illustrated Guide to Recurrent Neural Networks. LSTMs and GRUs were created as the solution to short-term memory. They have internal mechanisms called gates that can regulate the flow of information. These gates can learn which data in a sequence is important to keep or throw away. By doing that, it learns to use relevant information to make predictions. Almost all state-of-the-art results based on recurrent neural networks are achieved with these two networks. You can find LSTMs and GRUs in speech recognition models, speech synthesis, text generation. You can even use them to generate captions for videos. Okay, so by the end of this video, you should have a solid understanding of why LSTMs and GRUs are good at processing long sequences. I am going to approach this with an intuitive explanation and illustrations and avoid as much math as possible. Let's start with a thought experiment. Let's say you're reading reviews online to determine if you want to buy a product. When you read the review, your brain subconsciously only remembers important keywords. If your goal is trying to judge if a certain review is good or bad, you pick up words like amazing and will definitely buy again. You don't care much for words like this, gave, all, should, etc. If a friend asked you the next day what the review said, you wouldn't remember it word by word. You might remember the main points though, like it was a perfectly balanced breakfast. The other words would just fade away from memory, unless of course you're one of those people with perfect memory. That is essentially what an LSTM and a GRU does. It can learn to keep only relevant information to make predictions. In this case, the words you remember made you judge that was a good review. To understand how LSTMs or GRUs achieve this, let's review the recurrent neural network. An RNN works like this. First, words get transformed to machine-readable vectors. Then, the RNN processes the sequence of vectors one by one. While processing, it passes the previous hidden state to the next step of the sequence. The hidden state acts as the neural network's memory. It holds information on previous data that the network has seen before. Let's zoom into the cell of an RNN to see how the hidden state is calculated. First, the input in the previous hidden state is combined to form a vector. That vector now has information on the current input and the previous inputs. The vector goes through the TAN activation, and the output is the new hidden state, or the memory of the network. The TAN activation is used to help regulate the values flowing through the network. The TAN function squishes values to always be between -1 and 1. When vectors are flowing through a neural network, it undergoes many transformations due to various math operations. So imagine a value that continues to be multiplied by, let's say, 3. You can see how some values can explode and become astronomical, causing other values to seem insignificant. Let's see what a TAN does. A TAN function ensures that the values stay between -1 and 1, thus regulating the neural network's output. So that's an RNN. It has very few operations internally, but works pretty well. RNN uses a lot less computational resources than its evolved variants. Let's take a look at LSTMs. An LSTM has the same control flow as a recurrent neural network. It processes data sequentially, passing on information as it propagates forward. The difference are the operations within the LSTM cells. These operations are used to allow the LSTM to forget or keep information. Now looking at these operations can get a little overwhelming, so we'll go over this one by one. I want to thank Chris Ola, sorry if I butchered that name. He has an excellent blog post on LSTMs. The following information is inspired by his exceptionally written blog post. I'll include the links in the description. The core concepts of LSTMs are the cell states and its various gates. The cell state acts as a transport highway that transfers relative information all the way down to the sequence chain. You can think of it as a memory of the network. Because the cell state can carry information throughout the sequence processing, in theory, even information from earlier time steps could be carried all the way to the last time step, thus reducing the effects of short-term memory. As it goes on its journey, information gets added or removed to the cell state via gates. The gates are just different neural networks that decide which information is allowed on the cell state. The gates learn what information is relevant to keep or forget during training. Gates contain sigmoid activations. A sigmoid activation is similar to the tan. Instead of squishing values between -1 and 1, it squishes values between 0 and 1. That is helpful to update or forget data because any number getting multiplied by 0 is 0, causing values to disappear or be forgotten. Any number multiplied by 1 is the same value, therefore, that value stays the same or is kept. The network can learn what data should be forgotten or what data is important to keep. Let's dig a little deeper into what the various gates are doing. So we have 3 different gates that regulate information flow in an LSTM cell: a forget gate, input gate, and output gate. First, we have the forget gate. This gate decides what information should be thrown or kept away. Information from the previous hidden state and information from the current input is passed through the sigmoid function. Values come out between 0 and 1. The closer to 0 means to forget, and the closer to 1 means to keep. To update the cell state, we have the input gate. First, we pass the previous hidden state and the current input into a sigmoid function. That decides which values will be updated by transforming values to be between 0 and 1. 0 means not important, 1 means important. You also pass the hidden state and current input into the tan function to squish values between -1 and 1. This helps regulate the network. Then you multiply the tan output with the sigmoid output. The sigmoid output will decide which information is important to keep from the tan output. Now we should have enough information to calculate the cell state. First, the cell state gets multiplied by the forget vector. This has the possibility of dropping values in the cell state if it gets multiplied by values near 0. Then we take the output from the input gate and do a point-wise addition, which updates the cell state to new values. This gives us our new cell state. Last, we have the output gate. The output gate decides what the next hidden state should be. Remember that the hidden state contains information on previous inputs. The hidden state is also used for prediction. First, we pass the previous hidden state and the current input into a sigmoid function. Then we pass the newly modified cell state to the tan function. We multiply the tan output with the sigmoid output to decide what information the hidden state should carry. The output is the hidden state. The new cell state and the new hidden state is then carried over to the next time step. For those of you who understand better through seeing code, here is an example using Python pseudocode to showcase the control flow. First, the previous hidden state and the current input gets concatenated. We'll call it combine. Combine gets fed into the forget layer. This layer removes non-relevant data. Then the candidate layer is created using combine. The output holds possible values to add to the cell state. Combine also gets fed into the input layer. This layer decides what data from the candidate layer should be added to the new cell state. After computing the forget layer, the candidate layer, and the input layer, the cell state is computed using those vectors in the previous cell state. The output is then computed. Pointwise multiplying the output and the new cell state gives you the new hidden state. That's it. The control flow of an LSTM is simply a for loop. The hidden state outputted from the LSTM cell can be used for predictions. Using all those mechanisms, an LSTM is able to choose which information is relevant to remember or forget during processing. So now we know how an LSTM works, let's look at the GRU. The GRU is a newer generation of recurrent neural networks and is pretty similar to an LSTM. GRUs got rid of the cell state and used a hidden state to transfer information instead. It also has 2 gates, a reset gate and an update gate. The update gate acts similar to the forget and input gate of an LSTM. It decides what information to throw away and what new information to add. The reset gate is a gate used to decide how much past information to forget. So that's a GRU. GRUs has less tensor operations, therefore they are a little speedier to train than LSTMs. Researchers and engineers usually try both to determine which one works better for their use case. To sum this up, RNNs are good for processing sequence data for predictions but suffer from short-term memory. LSTMs and GRUs were created as a method to mitigate short-term memory using a mechanism called gates. Gates are just neural networks that regulate the flow of information being passed from one time step to the next. LSTMs and GRUs are used in state-of-the-art deep learning applications like speech recognition, speech synthesis, natural language understanding, etc. If you're interested in going deeper, I've added links in the description on some amazing resources that can give you a different perspective in understanding LSTMs and GRUs. I had a lot of fun making this video, so let me know in the comments if this was helpful or what you would like to see in the next one. If you liked this video, please subscribe for more AI content. Thanks for watching.